Hi, everybody. Welcome back to the Feynman technique. Today, we are going to be proving this identity using nothing but first semester calculus and a little bit of algebra. It turns out there is a way to do that. The steps seem a little bit magical, and I'll admit that I reverse engineered this strategy. But this is going to be a process that is 100% understandable and able to be followed by somebody with nothing but a level of knowledge up to first semester calculus. So let's get started. So the first thing we're going to do is introduce this integral u to the negative 1/2 um, over u plus 1 du. And I'm not going to go through the process of solving that. That is equal to pi over 2. All right. Now our next step, let's go ahead and figure out some other way of writing. Well, no, you know what? Actually, let's just go right for the substitution. So we know that this is true. Okay, we know this is true. All right. So now let's make the substitution u is equal to x to the b. And the motivation for that is, of course, because we have an x to the b here. Okay, so I'd like to replace this u with an x to the b, and then we'll figure out the rest later. Well, that's going to imply that du is equal to b times x to the b minus 1 dx. All right, let's perform that substitution. All right, our bounds of integration are not going to change. Um, our x is just going to be, well, it's going to be u to the 1 over b. 1 to the 1 over b is 1, and 0 to the 1 over b is 0. So our u is x to the b. So that's going to transform our u to the negative 1/2 into x to the negative b over 2. And of course, our u is x to the b. That was the substitution. And our du is equal to this. And now you'll note, now I just want to show you that no matter what value of b we pick, well, actually, negative values are going to mess that up. But no matter what value of b we pick, it's going to be equal to pi over 2. Okay, so let's just go ahead and reassemble our equality here. And all right, now what should we do? Let's clean this up a little bit. We have common bases here, so let's see, that's going to be b minus 1 there, right? We're just adding the exponents together. All right, now let's combine this into one fraction. So this is going to be 2b over 2. This is going to be 2 over 2. So we have 2b minus 2. Now we can get rid of this. And then minus b. Now we can get rid of this. And then, of course, we have this b, which we will put over here. All right, so did we do everything correctly? I believe we did. Yeah. Okay, but I'd like to do something else also. You'll notice that this pi over 2b can just be expressed as pi over 2b times 1, right? Well, 1 is the same as sine of pi over 2, right? Yeah, of course it is. So it's also the same as sine of pi b over 2b, right? Of course. Of course it is. Okay, so now we're here. All right. Now, where do we go from here? Well, hmm. What we'll do is this. We're going to multiply both sides of this equation by 2. So we multiply both sides of the equation by 2 and we get this. All right, next, we can just rewrite two of these integrals as this integral plus this integral. So we have this plus this. All right, So next, what I'd like to do is take our take this integral and bring x to 1 over x. All right, we could do another substitution, but I think it's simple enough just to bring x to 1 over x. No, in fact, that's not what we're going to do. Because you notice we have to somehow introduce a parameter a, don't we? Well, let's see if there's two different ways we can express b minus 2 over 2 in terms of a. Well, obviously, the first thing we could do is just let a equal b minus 2 over 2. Simple enough, right? Okay. Well, this is going to imply, let's just do some algebra right now. Let's solve this for b in terms of a. So we multiply both sides by 2. And then we add 2. So b is equal to 2a plus 2. All right, great. But what else can we get from this? Well, given that we started with this, all the rest follows. Just copy this over here, and now we'll subtract a from both sides. That's going to give us an a over here and a minus a here. And now let's subtract 2 from both sides. So we have minus 2. Well, you'll notice that a is both equal to this and this. That means that this, given our original equality a is equal to b minus 2 over 2, it follows that b minus 2 over 2 must also be equal to b minus a minus 2. So now we have two different ways of expressing b minus 2 over 2 in terms of either a or a and b. All right, so now let's copy this down here, and we'll use b minus 2 is equal to a right here. And then we'll use our other equality, b minus 2 over 2 is equal to b minus a minus 2 on this one right here. And then, well, I'd like to introduce a into what this integral is actually equal to. So let's go ahead and use b is equal to 2a plus 2 right here. So b is equal to 2a plus 2. Sorry, I should have used parentheses there. And now we can divide the top and the bottom of this fraction by 2. That's just going to give us an a plus 1 over b. So pi a plus 1 over b. All right, great. So now what I'd like to do is bring this, I would like to bring x to 1 over x in this expression right here. So doing that, we're still going to get 1 here, and now 1 over 0 is infinity, and it's just going to introduce a negative sign into all our exponents on x. So we have x to the negative b, and don't forget, given that we're bringing x to 1 over x, that's going to introduce the differential minus 1 over x squared dx. All right, we will use this negative sign to flip the bounds of integration, and we will distribute this x squared in the denominator. So we have x squared, and then we'll just have a 2 minus b. Okay, great. So that's true. Next, let's multiply the top and the bottom of this equation by x to the b minus 2. Okay. We'll copy that up here, x to the b minus 2. All right, what's going to happen downstairs? Well, we're going to add b and subtract 2 from all of our exponents. So adding b is going to get rid of this, and subtracting 2 is going to get rid of this, just giving us x to the 0. So that's just going to be 1. Then adding b is going to give us a b plus 2, and then subtracting 2 is just going to give us x to the b. All right, and to make it match the other side, we'll call this x to the b plus 1. All right, so now we have to be careful here. What are we doing? We're adding a b. All right, we already have a minus b here, so that's just going to get rid of that. This and this cancel. So now we're subtracting a 2 but we already have a 2 added, so this and this are going to cancel, giving us nothing but x to the a. Great. And now we are done. You'll notice we have the same integrand here. And we have our first integral going from 0 to 1, and our second going from 1 to infinity. That means we can simply write this as one integral going from 0 to infinity. And we are done. So there you go, guys. A proof of this integral identity using nothing but simple first semester calculus and some algebra. Hope you enjoyed that. We'll see you next time.